Now let's take a look at the first basic integration technique, and that is substitution. We use this technique when the integral that we are working with looks a little bit too complicated or too hard than we would like it to be. That's when we use this sub technique to simplify the integral. So let's try it on this example right here. So here we have an integral of cosine of 7 theta plus 5, and we know that this is a function of theta. The only variable that we have here is theta, and now we need to integrate this function with no boundaries, no starting point, and no end point, which means that this is indefinite integral. So let's make a note right here. This is indefinite integral, and we know it's going to be equal to the antiderivative of f, big F, of theta plus c, a constant. And now we need to integrate this term, cosine of 7 theta plus 5. However, we feel that the inside of this cosine is a little bit too complicated. So let's use substitution technique here. What about we set the inside of this cosine to be just one variable? So this one inside, let's set it to be just u. And now we have this condition, u equal to 7 theta plus 5. And this is our main substitution here. So main sub right here. And now the integral is equal to integration of this cosine, but the inside we change it to u, just one variable, and d theta stays the same. And once again, no boundaries, nothing right here and nothing right here. And now we need to integrate cosine of u with respect to theta, which doesn't really make sense, right? Integrate a function of u with respect to theta, it's different variables. So what you see right here, this one is a function of u. But what you have right here is theta. So we can't just integrate this, we have to do something with this d theta. So for now, let's work on the main sub. We know that u is equal to 7 theta plus 5. What about I find this? Du by d theta. I'm going to diff u with respect to theta. It's going to be equal to. So I diff these two terms with respect to theta. Diff 7 theta with respect to theta, I get 7. And diff 5, this is a constant. It goes to 0. And from this, I know that d theta is equal to du divided by 7. Let's make a box around this. D theta equal to du divided by 7. What about I put it over here? D theta. Same term. So now our integral becomes this, equal to same integral, cosine of u, and now d theta is equal to du divided by 7. And now with this constant, this 7 can be moved to outside of the integral. And now we have this equal to 1 over 7 times integral of cosine u du. So now we need to integrate cosine u with respect to u, and now it makes sense, same variable. So it's going to be equal to 1 over 7, and now we find the antiderivative of cosine of u, and that is sine of u. You need to diff sine of u to get cosine of u. So here we have sine of u. And don't forget this, plus c, a constant, at the end of indefinite integral. And that is the answer for the first example here. Now let's move on to this one on the right hand side. And here we have an integral of these terms, 3x squared times square root of x cubed plus 1. And this is a function of x, f of x. Which also makes me realize that we have a typo here. So this is not supposed to be dt. This is supposed to be dx, differential x. And now we find the integral of this function from -1 to 1, which means that this one is definite integral. Let's make a note. This one is definite with the boundaries. So I have this term, 3x squared, and x cubed plus 1, which look a little bit too messy for my taste. So I'm going to have to do something to simplify them. However, I can only pick just one of them to use sub technique on. So which one is it going to be? This 3x squared or this x cubed plus 1? One guideline to decide on this is to pick the one that looks more complicated. As you can see here, x cubed plus 1 is inside the square root. It looks more complicated than just the 3x squared that is outside. So what about I pick this one, the one inside the square root, to be the main substitution. So now we have u equal to x cubed plus 1. Our main sub here. And now this whole term becomes u, just one variable. And now our integral becomes this, equal to integral of the same boundaries from -1 to 1. Now 3x squared stays the same, nothing changes here. And square root u right here. And now the last term doesn't change, so we have dx at the end. And it looks like we have a little bit of a problem here. We have these terms, which includes both x and u, which means that we cannot integrate this directly. And we also have dx right here, which is not the same variable as the new one, u. So we have to do something about this. And now we move back to the main sub. Let's work on that. We find du by dx. We diff u with respect to x, so it's going to be equal to. Now we diff these terms, x cubed plus 1. You diff x cubed with respect to x, we have 3x squared. You diff 1, it goes to 0. By moving things around, we also know that dx is equal to du divided by 3x squared. Now let's make a box around this. Dx equal to du divided by 3x squared. And it's going to be the same as this dx right here. So let's put all these terms to dx. Let's put it back. And now our integral becomes this one, equal to, same integral from -1 to 1. 3x squared stays the same. And we still have square root of u. But right now, dx is equal to du divided by 3x squared. And for some reason we got lucky here. This 3x squared can cancel with this one down here. So in the end we have this equal to integral from -1 to 1 square root of u times du. So we need to integrate this square root of u with respect to u. No problem now. Same variable. So this square root of u is equal to u to the power of 1 over 2. So this is going to be equal to antiderivative of u to the power of 1 over 2. So it's going to be u with the power increased by 1. So we have u to the power of 3 over 2. And we divide same number down here. And we need to evaluate this term at two values, at the starting point, at the end point. At x equal to -1 and x equal to 1. Keep in mind that this -1 right here is x value, x equal to -1, starting point. And this one right here, also x value, the end point. So this is starting point x equal to -1 and end point x equal to 1. However, inside this term we have u, which means that we cannot use the x values that we have here right away. We are going to have to change u back to x. And we know that u is equal to x cubed plus 1. So let's use this. So this is going to be equal to, u is equal to x cubed plus 1 to the power of 3 over 2 divided by 3 over 2. And now we evaluate this at two values of x equal to -1 and x equal to 1. And now no problem, we have x inside this term. So what we just did right here is we sub back. So sub back, so that we have x variable back. Now let's continue down here. Let's evaluate this. Equal to. And now the endpoint, x equal to 1, goes in right here. So the first term, 2 over 3, which is 3 over 2 gets flipped up. And now we have 1 cube plus 1 to the power of 3 over 2 minus the antiderivative evaluated at the starting point, which means that this x equal to minus 1 goes in right here. So we have 2 over 3 times minus 1 cube plus 1 to the power of 3 over 2. So this first term right here is antiderivative evaluated at the endpoint, big F, at x equal to 1, minus the second term, the antiderivative evaluated at the starting point, big F, at x equal to minus 1. And now these two terms, 1 plus 1. We have 2 here. What about these two? Minus 1 plus 1, we have 0, which means that this whole term right here is going to go to 0. So we only have just the front term here, equal to 2 over 3 times 2 to the power of 3 over 2. And that's equal to 2 over 3 times 2 square root of 2. And in the end, we have this equal to 4 square root of 2 divided by 3. And that is the answer for this example. Now last example of this slide, this one down here. So we have an integral of 2z divided by cube root of z squared plus 1. And this is a function of z. And now we need to integrate this function with respect to z. As you can see here, this integral has no boundaries, no starting point, no end point. So this one is indefinite integral. Indefinite, which means that we can expect a constant c at the end. And as you can see here, this function is a little bit too complicated and messy for us to handle directly. So we are going to simplify this using the sub technique again. And now I have to pick the terms that I want to perform the sub on. What about these terms down here? Z squared plus 1. It looks messy because these terms are inside the cube root. So let's simplify this. U equal to z squared plus 1, our main sub here. And now our integral becomes integral of 2z, nothing changes here, divided by the cube root of the new variable, which is u. And dz stays the same, back here. And as you can see here, we have all these variables, z right here, and then we have u down here, and then another z right here. They're all mixed up, so we can't perform the integration right away. So we have to do something with this. And once again, we move to the main sub that we have right here. We find this, du by dz. Let's diff u with respect to z. So diff these two terms, z squared plus 1. So equal to, diff z squared with respect to z, it becomes 2z. Diff 1, it goes to 0. And from this, we also know that dz is equal to du divided by 2z. Let's make a box around this. And this is the same term that we have right here, dz. So let's put that in here. And now the integral is equal to integration of 2z divided by cube root of u, the new variable. And now dz is equal to du divided by 2z. And once again, we got lucky here because this 2z can cancel with this one. What about we continue over here? And now our integral is equal to integration of 1 over cube root of u, and back here we have du alone. So we need to integrate this 1 over cube root of u with respect to u. And once again, I want to express this function as a simple power. So let's do this. Equal to integration of u to the power of minus 1 over 3. And now du at the end. And the result is right here, equal to. Now we find the antiderivative of this u to the power of minus 1 over 3. So it has to be the same polynomial term, u to the power of something. And now the power has to increase by 1. It used to be minus 1 over 3, and now it becomes 2 over 3. And now we need to divide that number down here, 2 over 3. And since this is an indefinite integral, we don't have the boundaries. So in the end, we have this plus c instead, plus a constant. It looks quite good now, but we can't answer like this because this is still in terms of u, the new variable that we put in. The original function is in terms of z, so let's put that z back in here. And we know that u is equal to z squared plus 1. So let's put it back in. So this is going to be equal to 3 over 2 times z squared plus 1 to the power of 2 over 3 plus a constant c right here. And it's also equal to 3 over 2 times cube root, big one right here, of z squared plus 1 with the square inside. And don't forget the constant c at the end. And that is the answer for this last example here. The first basic application of integration is to use a definite integral to find the mean value of a continuous function whose function value changes continuously. Now let's take a look at an example down here. We have this function of f of x equal to square root of 4 minus x squared over this range from minus 2 to 2, which corresponds to this blue curve right here. And as you can see, the function value starts out at 0 right here. And it changes continuously along the curve. It goes up to the top and then comes down to 0 once again right here. And now we want to find the average value of all these different function values along this continuous curve. And since this curve is non-linear, the average value may not be right in the middle. So how are we going to find that one average point? This is the idea. The area under the average value must be equal to the area under the function f of x itself. So make a box around this. And this is the key idea for finding the average value of a continuous function. Before we continue, let's assume this average value to be a bar, a constant. And now let's try to translate the key idea that we have here, this equation, to be in terms of integrals. The first one that we have here is the area under the average value, and that corresponds to this integral. Integration of a bar, the average value, a constant, with respect to x. From a starting point, let's assume it to be a. To an endpoint, assume it to be b. And this has to be equal to the second integral, which is the area under the function itself, f of x. And that corresponds to this integral. Integration of f of x with respect to x and it begins at the same starting point A and stops at the same endpoint B. And now one thing we know about this A bar is that it's a constant. An average value is a constant, just one value, which means that we can move it outside the integral. Let me continue over here on the right hand side. So A bar is outside, and then we have this integral of just dx from A to B. And now it's equal to, on the right hand side, everything stays the same. So we still have this integral of f of x with respect to x from the same A to B. Now let's take a look at this term right here, this integral. What is it equal to? So here we want to integrate this dx right here, a really small step in x direction, starting from A to B. So very small step starting from A and go all the way to B. So in the end, this is basically the length from A to B. So what we have right here is going to be equal to B minus A. So down here we have A bar times B minus A equal to, the right side is still the same, integration of f of x dx from A to B. And now I move B minus A to the other side. So I have this A bar, the average value, equal to 1 over B minus A times this integral, same one, f of x dx from A to B, and make a box around this. This is the same formula that we have up here for finding the average value of a continuous function. And it all comes down to this key idea right here. The area under the average value has to be equal to the area under the function curve f of x itself. Now that we know where the formula came from, let's use it to solve this example down here. So we have the expression of f of x ready to be used, this one. And we also know the range, the interval, from -2 to 2. So this one is the starting point, A, and this one is B at 2. So let's use our formula right away. A bar equal to 1 over B minus A. B is 2 minus A is -2. So we have -2 right here. Integral from the starting point -2 and ends at endpoint 2 of f of x, which is square root of 4 minus x squared. Integrate this with respect to x. These terms right here are going to be equal to 4. And now we have to find the antiderivative of the square root of 4 minus x squared. But the bad news is, at this point, we cannot solve this integral yet. And that is because we need to know integration by parts in order to do that. So make a note right here. To solve this, we need integration by parts, which we are going to learn in the next couple of weeks. So this means that we sort of got stuck here. We cannot solve this. However, we also know that this integral right here represents the area under the function itself, f of x. And that corresponds to this region. This one under f of x. Under the curve, but above x-axis. And obviously, this is half a circle right here. So this box right here is going to be equal to half area of a circle equal to 1 over 2 times pi r squared. And we know that r right here is equal to 2 over here. So let's put everything in. So this is going to be equal to 1 over 2 times pi 2 squared. And that is equal to 2 pi. So this box right here equal to 2 pi. Now back to our formula. A bar equal to 1 over 4. Now times the box, which is equal to 2 pi. So in the end, A bar is equal to pi over 2. And that is the average value of this function f of x over this range from -2 to 2. And that is how you use a definite integral to find the average value or the mean value of a continuous function. In this slide, we want to find the area of the region enclosed by this continuous function f of x and the x-axis. Of course, we know right away that this is about definite integral that we have to solve here. Before we continue, I have the curve of this f of x plotted out on this graph on the left-hand side. But let's assume that we are not seeing this right now. So, not seeing this right now. Now back to the problem. Since we know that this is about a definite integral, let's build one. So we have this integration of this function f of x, which is x cubed minus x squared minus 2x. We integrate this with respect to x. It begins at a starting point, which we don't know what that is yet. A right here is unknown, equal to what? And the end point, we don't know that either. B right here is also unknown. Now let's make a box around this. Since we don't know the starting and the end points right now, it means that we cannot perform the definite integral yet. So the first thing we are supposed to do here is to find A and B. And we can find them from where the function curve f of x crosses x-axis. And this corresponds to the points where f of x is equal to 0. So we have this equation right here, f of x, which is equal to x cubed minus x squared minus 2x must be equal to 0. And now we take the common term x outside, and we have this left, x squared minus x minus 2 equal to 0. And now we factorize the back term, and we have this x minus 2 times x plus 1 equal to 0. From this, we know that this equation is true when x is equal to first point minus 1, second one is 0, and the last one is 2. So 3 points. And these points are the crossings of x-axis. And now let's try to predict the shape of our function f of x by using the information that we just got. So let's do that over here on the left-hand side. Let's have x-axis right here. And now let's assume 0 to be here. And then we have 1 right here and 2 right here. And we also have minus 1 right here. From the equation that we just solved, we know that the crossings happen at 3 points. The first one at minus 1 right here. Second one at 0. And the last one at 2. And now we check the asymptotic behaviors of this function. When x goes to positive infinity, we want to know what's going to happen to this function right there. And also when x goes to negative infinity, what happens there? So let's start with this one. X goes to negative infinity. Let's find out. Now back to the function f of x up here. As you can see here, the dominant term is this term right here, x cubed with the highest power. From this dominant term, we know that when x goes to minus infinity, then x cubed goes to minus infinity too. And it means that f of x goes to minus infinity as well. What about the asymptotic behavior on the other side? When x goes to positive infinity, what's going to happen? Let's take a look at the dominant term again. When x goes to positive infinity, then x cubed goes to positive infinity, and this means that the whole function follows this dominant term. It goes to positive infinity too. And now we know that on the left-hand side, when x goes to negative infinity, the function value becomes really large and negative. And I can use this point right here to represent that. Now on the right-hand side, when x goes to positive infinity, the function value becomes really large, and once again I can use this point around here to represent that large and positive number. So these two are the asymptotic behaviors at minus infinity and positive infinity. So let's start right here at this point on the left. Our function curve has to go up and up so that it can cross the x-axis at x equal to minus 1. And once it does, it has to keep going up like this. But then we know that this function curve has to cross the x-axis again at x equal to 0 right here. This means that this function curve has to turn at some point like this, and then come down to cross the x-axis at x equal to 0. And once it does, it's going to keep going down. But once again, we also know that this curve has to cross the x-axis again at x equal to 2, right here. Which means that this curve cannot just go down. It has to turn at some point like this, and then go up to cross the x-axis at x equal to 2. And after that, it can keep going up to positive infinity, the asymptotic behavior on the right-hand side. So what we have right here is the prediction of the function curve f of x from the information that we got from the calculation only. And now let's compare it to the actual graph of f of x up here. As you can see, these two are quite close. Our prediction captures most of the important characteristics of the actual graph. For example, the asymptotic behavior on the left-hand side, this point, minus infinity, just the same as what we have down here. And now on the right-hand side, the asymptotic behavior is this point, positive infinity, same down here. And now the crossings of the x-axis right here, the first one at minus 1, and this one at 0, and the last one at 2. Just like what we have down here, minus 1, 0, and 2. So we can use either one of these, whether it's the actual graph, number 1 right here, or the predicted graph down here, for this problem. And now back to the problem itself. What do we need to find? We need to find the area of the region enclosed by this function f of x and the x-axis. And that corresponds to this region, this one, between the function and the x-axis, and also this one down here. And it's going to be similar down here, this small region, plus this region right here. Before we continue, let's assume that the area of the first section is A1. So this is A1, and same thing down here, A1. And now for the second section, we name it A2. The area of this is A2. Same thing down here, A2. And now it means that our main goal is to find A1 plus A2. So let's continue our calculation down here. We had integration of x cubed minus x squared minus 2x. This is f of x. We integrate this function with respect to x. And from before, we didn't know the starting and the end point. So we had this a and b, which were unknown. Now the question is, what values should we assign to a and b? Let's take a look at the graph before we decide on this. As you can see, the region starts at this point, x equal to minus 1. And it ends at this point, 2. Well, does this imply that a has to be equal to minus 1? And b has to be equal to 2 right away? Let's check on this. If we choose to follow this, we are going to get this integral of x cubed minus x squared minus 2x with respect to x from minus 1 to 2. This means that we are going to integrate this function straight through from minus 1 to 2 right away. Now, before we continue, let's take a look at this. This is quite important. Let's take a look at A1 over here in this box and A2 down here in another box. In the first box, it's from x equal to minus 1 to 0. As you can see inside this box, the function value is positive. So let's make a note right here. Inside this box, f of x is greater than 0. And this means that the definite integral inside this box has to be positive as well. So make a note right here. This is very important. In this first box, integral is positive as well. Now for the second box, from x equal to 0 to x equal to 2. As you can see, the function value is under the x-axis, which means that it's negative. So we have this f of x is less than 0 inside this box. Therefore, the definite integral inside the second box is going to be negative as well. So make a note right here. Inside the second box, integral will be less than 0 as well. And this is where we have a problem. This means that the area that we calculate by using definite integral inside this box will come out to be negative. So from this, we are going to get area that is less than 0, negative. On the other hand, inside the first box, the definite integral is positive. So the area coming out of this is going to be positive. So for this one, area is going to be greater than 0, positive here. And these two, the first box and the second box, will cancel each other. And now we know that this is definitely not the way to go. And the reason is we have cancellation of positive and negative integrals. Knowing about these positive and negative integrals and how they can cancel each other, we have to find A1 and A2 separately. So the main guideline right now is find A1 and A2 separately. So we want to find this A1 plus A2, and it's going to be equal to the first integral, the first box of the same function x cubed minus x squared minus 2x with respect to x, the first box from minus 1 to 0. And now the second box, we have this integral of the same function x cubed minus x squared minus 2x with respect to x, and it starts at 0 and ends at 2. And since we know that the second integral that we have right here is from the second box, the result is going to be negative. So make a note right here. This one is going to be less than 0. And that's why we need to put this minus sign at the front so that it becomes positive. Now we can continue with the calculation. This is going to be equal to, now we find antiderivative of these terms, all of them. So the first one, it becomes x to the fourth, power increases by 1, and then I need to divide the same number down here. Minus second term, power increases by 1, it becomes 3. divide the same number down here. And last one, minus 2, x power increases by 1, it becomes 2, divided by 2 down here. And now I evaluate at two values, at minus 1 and 0. And I still have this minus sign right here, not changing it. Now back here, I have to find the antiderivative of these terms. And of course, it's going to be the same as the first one. So I have x to the fourth divided by 4 minus x cubed divided by 3 minus 2x squared divided by 2, evaluated at two values, from 0 to 2. Now this 2 cancels with this one, and same thing here, cancels. Let's continue down here, equal to, now the 0 goes in right here, here, and here, and everything goes to 0. So the first term equal to 0 minus the second term. Now minus 1 goes in right here, here, and here. And now we have the first term, 1 over 4, minus the second term, minus 1 divided by 3. Next term, minus 1. And that is the first integral. Okay, minus sign still here. And then the second integral, 2 goes in right here, here, and here. So we have 16 divided by 4 minus 8 divided by 3 and minus 4. And now the second term, 0 goes in here, here, and here. And of course, everything goes to 0 in this case. So we have minus 0 back here. And that is the second integral. Now, all these terms for the first definite integrals come out to be equal to 5 over 12. This one, 5 over 12. And all these terms inside the second box, this one right here, for the second definite integral, come out to be equal to minus 8 over 3. Let me continue right here on the left-hand side. It's going to be equal to 5 over 12 from the first integral, minus, and now from the second integral, minus 8 over 3. And just like we expected, the result from the second integral comes out to be negative. This one is negative as expected. And now the minus sign makes it positive, and we have this 5 over 12 plus 8 over 3. And this is equal to 3, 1 over 12 units squared. And this is the answer for this example.